Welcome to AI Trailblazers, Voices of Healthcare Innovators. I'm Matthew Ramsey.
Meta.
And I'm Emily Jo. As artificial intelligence transforms healthcare, we're engaging with today's leaders to uncover their groundbreaking work, learn from their visionary insights, and inspire the next generation to drive transformative efforts through the ongoing technological revolution in healthcare.
Today, we have the pleasure of speaking with Dr. Bradley Voytek, a distinguished professor at UC San Diego, whose groundbreaking work lies at the intersection of cognitive science, neuroscience, and data science. His lab focuses on using large-scale data science and machine learning to understand how brain regions communicate and how this communication changes with aging and disease. Dr. Voytek's approach combines theoretical and experimental methods, using both non-invasive and invasive techniques to study brain activity and cognitive phenomena. With a diverse background that includes being Uber's first data scientist and a passionate advocate for science communication, Dr. Voytek offers a unique perspective on the potential and power of AI in neuroscience. Today, we'll dive into his journey, research, and insights on the future of AI in neurology. Dr. Voytek, thank you so much for joining us today.
Thanks for having me, y'all. Appreciate it.
Yeah, we're so happy to have you, Dr. Voytek. And really, our first question is, you're at the forefront of cognitive science and neuroscience, and we would just love if you could share with our listeners, what was your journey going through cognitive science and neuroscience, and how did you lead into like AI? How did that happen?
You asked me to keep the question short. That's a really long answer. All right, I'll do my best. So I actually began my undergraduate career studying physics. I wanted to become a astrophysicist, and I got recruited out of high school to go into college a year early. So I skipped my senior year of high school and went to University of Southern California and was studying physics there in an ultra low temperature physics lab, making Bose-Einstein condensates, which I was 17, just turned 17. Didn't really understand anything that was going on. Was pretty overwhelmed. And long story short, ended up failing out of undergrad. I went to apply, register for classes in my third undergraduate year, and I was told I was no longer a student because I'd been on academic probation for too long. And this is in the late 1990s, early 2000s. And a lot of my friends who were older than me were computer science majors, and they graduated and gone on to really already careers that were paying far more than I thought was reasonable, more than I could imagine. I came from not a wealthy home by any means, and so I was like, well, that sounds pretty good. And so I got lucky. I begged and pleaded my way back in to get one more semester to try to get one more chance at my undergraduate career, and got very lucky that an undergrad advisor listened to me and gave me a chance. But she required that I switch my major. I could no longer be a physics major. She said, "That's not working for you." And so the only degree that I could finish on time was really psychology, given the courses I had taken. And that's partly because I needed to finish on time because it was an expensive private university, and I'd lost my scholarship because of the probation. And so I needed to get out of there as quickly as I could. So she helped me line up a lot of loans, and I took a bunch of psych classes, and then had a lot of free units left in the last like 2 to 3 semesters. And so to hedge my bets, I took some programming classes, intro to AI programming, which seems very forward thinking because that was 25 years ago. And in Lisp, which is an alpha programming language, I took a 2 unit like primer in Java, but the first one I took was like an intro to programming in C++ class. And I did that, like I said, to hedge my bets in case I, couldn't get a job with psychology. And so I had a bunch of math and stuff from my physics days, and I started taking some programming classes. I fell in love with the neuroscience side of psychology, and so I took some neuro classes, and then I took a couple of like philosophy of mind type of courses to fill out my degree just out of interest. And so I accidentally basically created a cognitive science degree. I didn't know cognitive science was a thing, but I took AI, philosophy, neuroscience, programming, math. That's basically and linguistics, right? And I took all of these, a computational linguistics class, and that was basically a cog sci degree, which my university didn't have at the time. And I really loved the interdisciplinary nature of it. And so that was my intro, was kind of an accident. I took classes that sounded fun and interesting to me after getting kicked out of undergrad in physics.
No, we love it. We love it. Thank you so much for your like honesty and like the transparency of your journey, right? Tell us a little bit more about this groundbreaking project, the Brain Scan R project, which you developed with your wife Jessica, and like how that influenced your approach to automated science and AI. We also have a slide that we'd love for you to discuss.
Oh, sure. Yeah.
Yeah.
That's funny, right? Because this is the project is kind of defunct now. We did this back in 2010. It's not dead. We're actually doing a much more sophisticated version of it right now. But this is one of the figures from the paper. And actually, this is a project that grew out of my frustration with trying to learn neuroanatomy, which I think it sounds like the three of you can maybe appreciate, given your studies right now. So I had the pleasure of doing my PhD at Berkeley and taking neuroanatomy, teaching neuroanatomy, I should say, with Professor Marion Diamond. She passed away a couple of years ago, but when I was a graduate student there at Berkeley in 2000, this is about 6 or 7, she was in her 80s. She'd been teaching at Berkeley neuroanatomy since well before my parents were born. And she was a phenomenal teacher. Actually, oh, hold on. She wrote this book, The Human Brain Coloring Book.
Wow.
Which is a fantastic resource for learning neuroanatomy. And so I got to teach her lab portion of this class with a really good friend of mine who she's now, after her PhD, she went on to actually do an MD as well and is like now an eye surgeon. But anyway, so Marion Diamond wrote this book, and I thought it was really funny because I go home over Thanksgiving to be with my family, and I'm like coloring as part of my homework to learn neuroanatomy. And it was really hard. And so as I was trying to learn more about the experimental side for my research on the neurosciences, I was really interested in how very focal brain lesions due to usually like stroke or some kind of traumatic brain injury impacted higher level cognitive functioning. In particular, I was focused on interactions between two brain areas called the prefrontal cortex and the striatum. And so in my naivete back then, in like 2005, 6, I thought, okay, surely there's like some kind of website or something I can go to, click on a brain region like the prefrontal cortex, and it'll tell me like the list of all the inputs and outputs and sort of the kinds of connections. Are they excitatory, inhibitory? What are the neurotransmitters and stuff? And that didn't exist. And so I spent months instead, like going back and forth down to the old library, like archives at Berkeley, reading these papers from the 1970s where they traced all the anatomy, trying to figure out all these inputs and outputs. And that drove me nuts. It was very frustrating. It felt super inefficient because anatomy is like a known thing. Is it connected or not? Like there is no uncertainty in there, right? Just tell me the nature of those connections. And so toward the end of my PhD, I was at a conference on a panel, and I made some passing comment that I believe that the neuroscience peer-reviewed literature is probably much smarter than we are. We just have to figure out how to extract that information from it. And there's a very eminent scientist from Stanford on the panel who like basically called me stupid and disagreed. And I sort of sat with this for a little while, and I was like, no, I'm pretty sure. And so this is around 2009, 2010. And I was sitting at home with my wife one night. We were watching Star Trek Deep Space Nine reruns. And I was like, this has been bugging me. I think I have an idea for how we could do some text mining of PubMed. So PubMed, I'm sure you're familiar with, is the sort of library run by the National Library of Medicine, part of the NIH, which is the database of peer-reviewed biomedical research publications. And they have what's called an API. So it's a service that you can use code to like make calls to the API, and it'll send you information back. And I said, I think we could do this thing where, like, if I do a search in PubMed for something like Alzheimer's disease, it'll show up a lot of papers, obviously, that talk about Alzheimer's disease, rightly so, but it'll also show up like a lot of papers that talk about tauopathy and memory and stuff like that, more so than it'll show up papers maybe, talking about, I don't know, hypokalemia or something like that, right? Which is not a cause of Alzheimer's disease, right? And so I was saying, I think if we just sort of hit this API and look at how many papers talk about like topic A and topic B together, we can get a sense of how strongly different ideas are related in the neuroscience literature. And I was a MATLAB programmer at the time during my PhD. My wife is a professional Python developer. And she challenged me to a code off. She literally said something like, "Oh, I could totally write that faster than you can." And so, long story short, she won, convinced me to become a Python developer after that. And we created this brain scan R project, which was just counting how often different ideas show up together. And so upper left was sort of the beginning of the next stage of this, which is we did this. We tried to publish this paper demonstrating this in peer review. Actually, skip to the bottom left here in the C where you can visualize a topic network. It used to be a website where you can go and you could type in a phrase, a word like serotonin, which is a neurotransmitter that a lot of people know because of its role, selective serotonin reuptake inhibitors, SSRIs, anxiolytic antidepressant. And so you can type in serotonin and you get this whole suite of brain regions that papers that talk about serotonin tend to talk about, hypothalamus, hippocampus, and so on, as well as different sort of psychiatric disorders, depression, anxiety, and migraine. I had no idea, but apparently serotonin, there's a lot of papers that talk about serotonin and migraines because certain kinds of migraines are treatable by SSRIs. And so we created this tool to visualize the sort of topic network. And then we could do some math and statistics on these graphs. And so we went to publish the paper and we showed like, hey, just by text mining alone, you could type in something like Parkinson's disease, which is one of the few neurological psychiatric disorders that we actually know what's gone wrong in the brain, right? In Parkinson's disease, you lose dopaminergic output neurons from the substantia nigra part of the brain, which leads to resting motor tremors and bradykinesia. Right? And so you type in Parkinson's disease and it comes back with Parkinson's disease is most strongly interconnected to, uniquely, motor control, dopamine, substantia nigra, and stuff like this. And we have to publish this, and peer reviewers are like, yeah, we know that these things are related already. I'm like, well, I know you know because you've been studying this for 30 years, but now math knows. Isn't that neat? Like we don't have to it can discover these patterns. And this is 2010, 11, and they just weren't really buying it. AI wasn't really quite the same. And so we tried to take it as next step further, which was this hypothesis generation model in the upper left. And the basic idea is we sweep through this graph of how all of these different topics and ideas are interrelated. And we find like a key term, like here term A, and we find instances in the graph where the key term is strongly related to two other terms who are then together weakly related. And so the example on the bottom right, we'll just skip to the bottom right to section D. So for example, if you put at the time, this is 12, 15 years ago, serotonin into this procedure, it'll show you approximately 5,000 papers that mention serotonin and this brain region called the striatum. And also on the other sort of right flanking arm there's about 3,000 papers that talk about migraine and the serotonin. And so given that strong link between serotonin and the striatum brain region and serotonin and migraine, thousands of papers, statistically speaking, you would imagine that there should be more papers talking about the brain region of striatum and migraine in the bottom right there than there actually are, right? So given the strength of the flanking arms, 16 is a very small number. And so we can algorithmically sweep through this graph to try and find these sort of weak points where there should be links, but there aren't. Now, this is pre-natural language processing, really. And so it very well may be that all 16 of those papers say there's absolutely zero link between the striatum and migraine. We didn't do any natural language processing, so we couldn't tell. But we are actually like currently right now, there's a data science PhD student in my lab who's working on sort of the next generation version of this that's far more sophisticated, using more modern tools to try and do this sort of data-driven discovery of topics in neuroscience.
Yeah, you kind of mentioned how like you used machine learning to determine how different neuroscience topics are related in PubMed, but how have y'all used like AI machine learning to better understand I guess how brain regions communicate, and I guess how have you used machine learning and AI to better understand, I guess, how the brain works?
It's kind of funny. We don't really use a lot of AI, strictly speaking. The only way that we use AI is we use LLMs to write doc strings for code for us. I don't know if you're familiar, but like when you write code, one of the things that you should be doing is like really giving good, clean, human level understandable documentation for it. And those are called documentation strings or doc strings. And so whenever we write functions that we're going to put out into the sort of like world of neuroscience, we'll often use LLMs to write those doc strings for us. That's pretty much the main use case of AI. But we do a fair amount of machine learning. And we can sort of quibble about the distinctions between machine learning and AI, but that's outside the scope of this. So what we're really fixated on, I would say, in my lab, is trying to figure out what kind of data and information we can extract out of the signals that we're recording from the brain. And so all of you have some, like, it sounds like very cursory, if not more advanced understanding of like neurophysiology, right? You're at least taking some neuro units and stuff. I don't know what your undergrad degrees are in, but you know that neurons, for example, are electrical signaling units in the brain. That's the primary way that the brain communicates. You've got 86 billion or so of these brain cells, and they send these action potentials. And like, do you know anything, like, what's like one or two things that you know about action potentials? Like
Sodium channels,
sodium channels,
saltatory conduction, myelination.
All right. So saltatory conduction, right? So these aren't passive processes, it's active process where the actual like voltage spike is propagated down the axon to the next neuron, which causes neurotransmitter release into the synaptic cleft, and it gets taken back up and so on, right? And these are within the computational neuroscience world where I spend a little bit more time. These action potentials are binary. They're all or nothing responses, right? So much so that you have the all or nothing law, which dates back, 100 and something years, that the way that neurons encode information that they receive from the external world is through spike timing and spike rates. How many action potentials per unit time? If you have a more intense stimulus, the neurons in the visual cortex fire more action potentials more quickly, right? And from that, we then derive collectively as a field these artificial neural networks. Right, we try and say, well, the brain is very good at learning new things. So what if we try and simulate the brain in these artificial units where you connect these like individual neurons that receive inputs and send outputs, right? Except the most effective deep learning algorithms that are out there right now don't use binary all or nothing spiking neural networks. They use more modern architectures with different what are called activation functions. So the neurons aren't all or nothing. They send these sort of ReLU or GeLU kinds of responses or what have you. And so one of the things that we do in my lab is we say, well, okay, let's look at the data that are coming off of our recordings. What information can we get? So, Charles, you mentioned that you have the different ion channels that are opening and closing that give rise to the action potential, right? And so sodium channels open, potassium channels close, right? And you get this sort of like dynamic, and the action potential waveform is just binarized into did it happen or not. And so one of the more recent projects that one of the PhD students in my lab, Blanca Martin Burgos, is doing right now is parametrizing each individual action potential's waveform shape down to like how quickly, like as the voltage begins to rise, what is the ramp of the voltage up to the inflection point at which the action potential initiates? How long does it take to go from that initiation point to the peak of the action potential? And then it has an exponential decay to this hyperpolarization. What is the shape of that decay curve? What is the voltage at which it hyperpolarizes before it settles back to sort of the resting membrane potential? And normally you can't do this because you action potentials last like a millisecond. And even most modern versions of exponential recording only really sample like 20,000 samples per second, which means a whole action potential is only 20 data points long. And so that's not enough data to like see the sort of fine scale waveform shape. And so we're working with collaborators who sample at 200,000 samples per second. So now an action potential is 200 samples long. And now you can see these like rich, interesting features in the waveform of each individual action potential. And it turns out that our results are suggesting, and the paper will hopefully come out next year, that neurons aren't binary. These aren't all or nothing action potentials. They actually have like very distinct, interesting waveforms that those waveforms systematically change shape as a function of the input that the system is receiving. And so sort of linking that back then to the machine learning, we use machine learning to take the features that are interpretable that we derive given our known fit. Like we know physiology, we know what's happening that causes an action potential. Just like in the heart, you know exactly where the P, the QRS, and the T complexes come from to give rise to these systematic waveforms in the electrocardiograph coming off of the heart, we know what is driving the shape of these individual like features on an action potential. So let's parameterize these like in a way, turn our data into numbers that make sense, right? Interpretable machine learning and AI, right? And then once we've got all those parameters, now we can do the machine learning and say, like, are there features that systematically change as a function of the state of the animal or the inputs or what have you? And then on the AI side, given what we're learning about how like maybe action potentials in real neurons are non-binary, can we create new AI architectures that are more biologically inspired and informed that don't assume binary all or nothing, but look more like what are actually the most successful AI architectures that we're using right now? So does that kind of make sense?
Yeah, that's so cool. And it actually works very well with our next question because, I think often a problem like a data science problem that starts to rear up as you get more and more data, more and more points, and when you're going from 20 to 20,000 data points, you're trying to, apply these models and, gain a little bit more understanding.
Right.
But then it comes to at a certain point, you aren't, reasoning through every single step of the way, but rather you have to trust your model. And can you talk about the challenges of that and how you can know that what you're getting out is actually reliable, and how maybe for neuroscience as a whole, how you can leverage these tools, but know that you're leveraging them in a way that's actually reliable.
That's a fantastic question. And so sort of the joke phrase in my lab is when in doubt, simulate. And so if you want to develop a new algorithm that purports to do something, right, you need to make sure that it's doing what you think it's doing. And so in the machine learning world, we'd say you need really good labeled training data. And you want to make sure that you can then your algorithm is doing what you want, and like successfully classifying states based upon labels and things like that. Biology doesn't come pre-labeled. And so training data, like knowing the ground truth reality in biology, is often impossible. We just don't know. We don't have good training data because evolution didn't label individual action potentials for us as being of one type or another, right? And so we will often then, in conjunction to the new algorithms that we develop, try and create simulation frameworks to simulate data that have known parameters where the data actually look like real data that we get from physiology. So just going back to the heart because it's a little bit more simple, right? So in the electrocardiogram for the heart, you do get these like P, Q, R, S, and T complexes. And like I said, we know exactly what each one of those represents. Opening and closing of different chambers and the like pumping of different chambers of the heart at different times, right? So you've got the systole and diastole for the closing, the opening. Did I get that right? The order right? The closing and the opening of the different chambers, right? Around the R peak, and we count the number of R peaks per unit time to get the RR interval, which is the heart rate, or the variability of that is heart rate variability, right? Done. Like we know the physiology of the heart. And so there's also really good tools for simulating like physiologically plausible heart signals. And so if we wanted to create a new algorithm for like, doing more for our heart data than just counting the number of R peaks per unit time, and parameterizing each individual heartbeat, which is, I'm saying this because this is something we're doing, then we can break down each P, Q, R, S, and T complex individual subcomponents, right? And so we know that there are certain disorders that are involved, like cardiac disorders that are associated with things like, a prolonged QT interval, right? These are like all very well known, very well replicated. But if you go to a cardiologist, the way that the cardiologist will measure these things, and I've seen it literally just weeks ago, what happens is they have a printout of somebody's ECG. They pull calipers out of their pocket and they measure on the printout the distance between the Q and the T interval or something like that, right? We could do better, right? We have code to do better, right? We can do this. And so we do sometimes have pre-labeled training data where, okay, we know that certain kinds of arrhythmias are associated with prolonged QT intervals. If we create a new algorithm for decomposing each ECG heartbeat into sort of interpretable features, we should also be able to, using machine learning, discover the relationship between prolonged QT intervals and certain kinds of cardiac disorders, right? Or like a flutter, or increased heart rate variability, or what have you, right? So we should be able to recapitulate those known clinical observations. Just like in the neurosciences, we should be able to recapitulate, given new algorithms for parameterizing each individual action potential, some of the very well-known things that, like, certain classes of neurons have wider action potentials than other kinds of neurons, right? We should be able to capture that. But also in conjunction, we should create simulation frameworks to simulate ECG signals or heart action potentials and so on. And our code should be able to also precisely capture the features that we simulated as well, right? And so for biology, you have to take this multi-pronged approach of taking the things that are really well obvious and known and making sure you can capture that, and also then simulating signals to make sure you can capture those simulated signals as well. Biology is real hard. It's real hard.
No, that's solid. Thanks for sharing insight on how you're taking this multi-layered approach towards like integrating AI with neuroscience. We kind of now want to talk about lateral and talk about your expertise from the industry. And for many of our listeners, Dr. Voytek is the first ever data scientist for Uber. Dr. Voytek, could you tell us a little bit more about that experience and maybe how that's shaped your insights into like healthcare translation to the work you're doing?
Yeah, so there's no obvious direct translation to healthcare, right? So I did my PhD in neuroscience at Berkeley. I was supposed to move to Germany for a job. I turned that job down because my wife and I decided we didn't want to leave California. And so I was at home, like having a barbecue dinner party with some friends, drinking beer and complaining that I've been in school for 20 something years and still don't have a job and don't know what I want to be when I grow up. Right? I'm like 28 years old or whatever it was. And one of my best friends from high school, I mean, I was the best man at his wedding. I drove him to school every day because I had the like working car. I practically lived at his house for a year because his mom was awesome. And my family was strange. And so I used to crash at his place all the time. He had dropped out of undergrad to do the startup tech thing, and he was in Seattle for a number of years. But he ended up moving to the Bay Area in 2008-ish, toward the end of my PhD in Berkeley. And so we used to hang out and like write code at coffee shops together, him for his companies that he was working for, the startups, and me for the neuroscience stuff. And he had just quit his previous job and started the startup. And he's like, well, he's at this dinner party and I'm complaining about this. And he's like, you did data stuff in your PhD, right? Like, I think, this new startup I'm working for needs like a data person. Why don't you come and talk to us? And so he was number 4 or something at Uber. He actually developed all the code that like lets the different phones talk to each other in order to sort of like deliver rides, like to pair drivers with clients. And so I met with their CEO at the time, and I got pulled in to develop their data strategy. How do we use data coming off of the phones in order to make Uber more profitable and more efficient? And so in the earliest days, it was mostly strategy of like, what could we do? How could we make this better? Right. And so like in taxis, unless there's a call to the central dispatcher, which doesn't happen very often, taxis just kind of drive around, and each driver uses their own knowledge of the city and intuition in order to try and find the places where they're more likely to get a pickup. Whereas when we've got the data coming off the devices, we can do predictions, right? And so, very naively, but intuitively, like 4 a.m. is not a very good time to be trying to, drive around and collect trips, right? Whereas, anytime in the afternoon and evening and night is a really good time to try and pick people up from an airport. And so we could use historical trends, which are these sort of fluctuating patterns of cycles, like peaks and troughs of demand over the course of a day and over the course of weeks and over the course of months to try and predict future demand. For any given point in space. At the time, it was only San Francisco, and there was only 10 drivers total driving for Uber, so it was pretty easy. But really early on, it became very clear also that we can't just rely on the historical data patterns. We also need to be pulling in other data sources. So like weather was like a very big prediction. If it was raining, many more people wanted to take trips with an Uber, so we needed to make sure we had more drivers to meet the demand. But then we ran into a couple of other issues of like, we talked about the Astros a little bit earlier, and baseball playoff season just started today. This is 2011 in San Francisco. The San Francisco Giants baseball team won the World Series in 2010, 12, and 14. So, 3 World Series in very quick time frame. So like the San Francisco Bay Area was really Giants baseball crazy. But baseball, I love it, but it's a really boring sport. It's long. There's 81 games played at home every year, 162 games total. It's a very long sport. So even like some of the most diehard fans, if your team is losing by 5 or 6 runs after like the seventh of 9 innings, people start to leave the stadium early. We need to make sure that drivers are available outside of the stadium as people start to leave, right? And so we realized we need to be pulling in real-time sports scores and weather data in order to try and like predict when and where people are going to want to take Ubers from, so that as soon as you open that phone to request a ride, there's a driver waiting right there for you. That's the ideal. As soon as you want a trip, a driver's there, right? That's the ideal. And we use data in order to do that. And so it became very clear that we need to be pulling in data from everywhere. We need to know for every city that Uber is in, like what concerts are happening and when, and how popular the concert's likely to be. Well, how do you get that? Let's scrape the number of Instagram followers that the people that are running the concerts have to try and get a sense of how popular they're going to be, so we can try and estimate demand, right? And so we built up these systems that were scraping in data from all over the place, not just Uber's data that they're collecting, but data from all over every resource, weather data, sports score data, concerts venue, tweets about different like locations in the city, whatever we could find in order to build these prediction models. And so, long story short, the leadership at Uber at the time and I didn't always see eye to eye on everything. I tried to quit. I renegotiated my contract, stayed with them as sort of a contractor for a couple of years, doing sort of like data-driven theory kinds of projects before starting my job as a professor here at UC San Diego. But one of the main things I learned, other than like how to write really good professional level, production level code, which I now can't do. I'm very like bad again. But was thinking about how do we solve problems using data and not constraining ourselves to just the data that we're collecting, but the massive amounts of other data that are freely available out there in the world. And can we use that to try and solve problems about the brain? So going back to that brain scanner project, we didn't collect any of that data. We just scraped that data from a database. Right? We use that same sort of ethos in my lab often. We'll run an experiment in our lab, but then we'll look for publicly available neuroscience brain data experiments that are out there to see if we can replicate our results using data from other research groups in other parts of the world collected for totally different purposes, right? And we really want to like try and bring as many different pieces of data to bear on the same problems as we can, because in theory, it should only get better when we attack it from multiple different angles.
Thank you so much for telling us about your Uber journey and what you did at Uber. That's super interesting. I feel like how often can we talk to the first like data scientist of such a big company? But kind of like looking ahead, like what does the future of AI and cognitive neuroscience look like for you? And what are you excited about? And kind of along those lines, what skills should students develop today to be a part of that next wave?
What does the future look like? I'll try that one first. So I think LLMs hopefully should change the way in a positive that we do science. So, maybe I'm a utopian, maybe I'm naively optimistic, maybe it's because I grew up watching too much Star Trek. But, like in Star Trek, you've got the Federation has these ships, and all these ships are driven by AI. Right? Like engineers that are working on these ships in Star Trek are talking constantly to the ship's computer, asking, well, hey, what about this problem? Can you help me with this? I'm stuck on this. Do you have any recommendations? Right? And so they're treating the AI as a very smart, very fast collaborator to bounce ideas off of. Right? And I really see that as what the future of AI and medicine and science should be. Right? So as clinicians, let's say you go into neurology. Right. And you've got a case with somebody that's had some kind of brain damage. You can see that they've got this like very everybody's brain damage is different, right? Like they have an MCA stroke, and that bleed is going to be different depending upon their individual morphology, right? You got the big artery feeding the brain, the MCA like this, and maybe it's just one part of it got damaged on one side and it took out part of the posterior parietal cortex, right? You have to make a judgment call then as a neurologist, as like looking at their scan and doing the neurology exam, right? The like all of the crazy stuff that entails the neurology exam entails, and you're trying to pinpoint what the deficit might be. Right? What if you could also simultaneously take that person's individual stroke pattern of damage, upload it into an AI system trained on brain data, and it says, based upon this pattern of brain data, we suspect that this person will have, a deficit in X, Y, and Z. And, this one is actually pretty subtle and difficult, but, maybe you want to begin training, and rehab earlier for this thing than this other thing, right? Just a smart collaborator that you could bounce these ideas off of, right? That's kind of the ideal that I think we should be going for in terms of LLM-driven, like generative AI driven, like medicine and AI, right? It's not doing clinical decision making for you. It's a colleague who has access to everything that can help you make better clinical decisions, right? And then you're still using your expertise and your conversations with that person and their families, trying to get a sense of what their day-to-day life changes are, in order to then bolster your predictions, right? Same with the sciences, right? What I want is, I still want, and we're building it now because I'm so frustrated 15 years later still, I want that website where I can go and click on the prefrontal cortex and it'll tell me this is the inputs, these are the outputs. These are the neurotransmitters that are primarily expressed. Here are the different genes that are expressed in this region, and here are the primary functions of the prefrontal cortex. Right? I want that. That's like the thing that I want. And then I want to be able to query that with an LLM and be able to say, okay, given everything we know about, the prefrontal cortex, are there any genes that are statistically over or underexpressed in the prefrontal cortex that we think are involved in memory that we haven't been really studying very much, right? That's all plausible given the data and the technologies we have available to us right now. It's just nobody's built it, right? And so we want to build that kind of thing. I want to be able to go to a website, to an LLM driven thing and say, show me all the parts of the brain that are most impacted by Alzheimer's disease. What are the genes that we know nothing about that are most strongly expressed there that like we just have very little information on, right? That will help me then guide my research, right? What are the primary neurotransmitters and secondary messengers involved in these Alzheimer's related brain regions? I don't know. Maybe there aren't any. I don't know. But like, we have the data, we can find out, right? We can use LLM to help us. And so that's kind of how I see things going, is building these tools to help complement our expertise in science and in medicine to facilitate either research or clinical decision making.
Yeah, I mean, that's fantastic. Thanks for painting the picture of really what neuroscience is and what it looks like. I think that's very practical and for not just this generation of providers, but our upcoming generation on how to think, how to approach such complex science this way. And so that was fantastic. Dr. Voytek, it has been an absolute pleasure speaking with you today. Your work at the intersection of AI, cognitive science, neuroscience, it's clearly pushing the boundaries of our understanding of the brain and how we can utilize data science to uncover its mysteries. Thanks for sharing your practical insights, innovative approaches, and most importantly, for radiating such passion with us today. The future of AI in medicine is bright, and it's leaders like Dr. Voytek who are paving the way for more equitable, efficient, and innovative healthcare solutions. Stay tuned for more thought-provoking discussions with the trailblazers who are driving this change. Until next time, keep exploring the frontier of AI in medicine. Thank you.
Thank you.